Bem-vindos à sessão Modernização Tecnológica, o caminho para o novo modelo de governação. Meu nome é Sandra Mateus e eu sou responsável pela gestão comercial do Ministério da Saúde na Microsoft e estou aqui hoje acompanhada pelo meu colega Miguel Barradas, o nosso Client Technology Lead, também no Ministério da Saúde, e pelo Gerard van der Berg, o nosso evangelista para os data centers da Microsoft. Nesta sessão vamos dar-vos um overview dos nossos data centers, que suportam os nossos serviços cloud e como um dos fatores mais relevantes da modernização tecnológica que influenciam também aquilo que é o modelo de governação das organizações de futuro e das organizações digitais. A apresentação do Gerard será em inglês, com legendas ao momento, para facilitar o entendimento de todos que possam acompanhar-nos aqui na sessão. Deixo também a nota que durante esta sessão podem ir fazendo as vossas perguntas no espaço de Q&A, podem fazê-las em português ou em inglês, e nós no final da apresentação abordaremos essas questões diretamente ao Gerardo, ou comigo, ou com o Miguel. Portanto, estejam à vontade para ir colocando as vossas questões. E sem mais demoras, e tendo em conta que é uma sessão que desperta bastante interesse, eu passo a palavra ao Gerard e vou fazê-lo em inglês. Welcome, Gerard. I've done the introductions in Portuguese, and the floor is yours. You can start now.
Okay, thank you, and a real warm welcome from myself here. Just a brief introduction. Yes, data center evangelist, right? And that's the role inside Microsoft that gives you the permissions to talk and explain a lot about the concept and the content around our data centers, around our facilities. And that's what I'm trying to do in the next roughly 90 plus minutes, giving you a bit of sense on when we talk about the cloud, what's basically underpinning all that infrastructure inside that cloud, what's running in it, and how, for instance, do we operate, how do we secure, how do we make sure that we reduce that impact on the environment, right? What are we doing in research areas to overcome the data gap, to make sure that we become even more energy efficient, to find new sources, to find new means of cooling principles, to all those concepts are part of the topics that I'm going through in roughly the next 90 plus minutes. And that's been explained by Sandra, right? Keep on posting the questions and we will definitely get back to the questions at the end of the sessions. Now, first of all, when we talk about global reach, it's to give you a bit of sense on global reach. Microsoft acts on a global corporate dark fiber backbone. And this is a static page. This static page over here, you see those dotted lines around the continents. That's the Microsoft dark fiber backbone. Now I'm starting up a different application here, but that is to give you a bit of sense on, when we talk about that backbone, it is globally connected with regions. It is a dedicated backbone of Microsoft. And that means that we don't use the public internet to connect our data centers, our regions. We don't use what we call virtual private network across the public carriers, like some others do. And don't get me wrong, right? They do encrypt, but they don't have their own network connectivity. Now, this backbone, you see different colors of icons, right? And the ones that are light blue are basically the active regions. For instance, West Europe. And that's in the region where I operate, around the city of Amsterdam, multiple data centers inside that region. Then you also see those grayed out regions. For instance, in Italy North. Those are the announced, soon to become alive regions. So you see a lot of coverage, but then you see those little blue dots, right? Very closely connected to the network. For instance, this one in Priovelo. That's what we call a network entry point, a point of presence. The points of presence are basically giving us as consumers the option to connect into the dark fiber backbone and then travel encrypted across the network into the closest by region, or obviously the region of preference. So you see a lot of global coverage, but you may have noticed as well that there are satellites around this animated globe. And that's not to make this animation look fancy, right? No. In the last quarter of 2020, we introduced the concept of Azure Orbital. And that is basically giving first organizations that do not own their satellites themselves, right, the option to basically subscribe into a window of time, into a satellite of a partner, capture information, send that information back to us. And then we collect that information into our own ground stations at our own facilities. That was Earth observation. But very soon after Earth observation, we started to also support the concept of global communications. Think in the space of IoT, connected cars, oil and gas, right? Oil rigs, very often disconnected, mining, right? Or transport. Think about the concept where network infrastructure at land is not there or not sophisticated enough. That's where you then can rely on, for instance, on Azure Orbital. And here you see again those ground stations at our facilities. So look at Azure Orbital for us as an extension of the already large scale dark fiber backbone, but giving customers the ability, when there is no network connectivity close by, to connect into that dark fiber backbone by using these communication services. And then we talked about regions working together, being connected with each other. That's part of what we call Azure reliability. And Azure reliability has different layers, so to speak, right? Think about what is done at Microsoft to make sure in case of a natural disaster. Think about earthquakes, large-scale tornadoes. Think about flooding, right? What do we do to make sure that there is an option to fail over from one region into another region? That's the concept when we talk about regional failover, regional redundancy. So if a primary region is failing, then the option to fail over into a secondary region is there. That secondary region obviously becomes then your primary region for a moment in time. You fail over with services, you replicate data. And a critical component here, excuse me, a critical component here is the design concept of data should not leave the country. That's the premier concept in the design principle. So data residency boundary. Data, very often, critical data, is not allowed to leave that boundary. And that's the design principle for region 1 and region 2 being in the same geographical data residency boundary. Now, when we step from a region redundancy into how do you make sure that we still have availability inside a single region in case of data center failure, right? We can go back 2 years ago when there was a data center failure at a hosting partner called OVH, a fire in Strasbourg, taking down a complete facility. Now, to make sure that that cannot happen in the concept of a region of Microsoft Azure is when we talk about availability zones. Now, there are some criteria for a region to support the concept of zonal redundancy. You need to have at least 3 zones inside a region. Those zones are logical zones, right? A logical zone can consist out of 1 or even more physical data centers. Each data center in that zone must be able to run completely independently on power, cooling, and network from the others. So when the services, the data of you is being replicated and synchronized continuously across those 3 zones, and zone 2 might fail, zone 1 and 3 will still continue to care of your access to the services. And that's why network latency is critical in a region. And I'll come back to somewhat more detail around network latency in the network segmentation. Now, then we step into a data center. How do we make sure that infrastructure failures inside a single data center do not take down access to services or data? Now that's when you start to look at the concept of an availability set. An availability set is what we call deployed across fault domains. Visualize a fault domain as a physical rack with its own core power, its own core network, and a lot of servers, 48 or 96, heavily depending on the type of servers. We use at least 3 of those racks, like behind me, to deploy your availability set across. So if one rack would fail, then still other racks take care of access. And another critical component here to understand is that when we talk about redundancy, right? And I've worked in hospitals. When we talk about redundancy, it's backup power, diesel backup generators, right? It's disaster recovery units. But in the concept of Azure as well, it's also software-defined availability. So software becoming more and more the predominant layer of management in case of a potential risk of failure. Now, and that is also related to when we talk about the different service models, the cloud service models, there are different layers of controls, management, responsibility at the customer side and responsibility at the Microsoft side. Those models we call the cloud service models. Now, the first one, right, the on-prem model, the customer is completely, you are completely in control. Absolutely, right? You manage, you control, but you also carry all the costs. You also carry the costs of the servers, the building, right? The power, the people, everything. When you move into the infrastructure, into the cloud, right? We start to manage, and we, Microsoft, start to manage more and more in the network, the storage, the server, and the virtualization. And the building is managed by us. Infrastructure on top, the customer is still managing that part. In platform as a service, when we talk about cloud native apps, right? You already see that we are, as Microsoft, start to manage more and more. You're still managing the concept and operating, controlling the concept of data and applications. In software as a services, right? Think about Teams, think about Office 365, Exchange, SharePoint Online. Pretty much everything is managed by us. And on purpose, I drew that blue box around data to make absolutely sure that we, as Microsoft, we manage the data, but we don't own. You are still the data owner, right? That's a critical component, right? Although you don't manage it, though we don't have insight, we manage it, you are still controlling it. Now, when you look at the different models in the concept of infrastructure as a service, platform as a services, and software as a services, there are some inherited industry benefits. And those are pretty much very important when you start to think about why should I even make that move into the cloud? Why do you have increased productivity and efficiency IT staff? Why? They can focus more on the real business benefits of an organization than just managing the bare metal, for all respect to managing bare metal, right? Because that's a critical component as well. Recovery time, right? Because the replication, the redundancy, the availability of having multiple different layers of data protection, and go back to the infrastructure savings. So those are just 3 of them. And that's to give you a bit of sense when we talk about those different cloud models. Now, I'm going to bring you back roughly 33 years in time when we started to design our first data center. In the last 33 years, we designed pretty much roughly 9 different types of generations. But the first generation was a traditional data center, like anybody else was building. Chilly inside, really cold temperature to cool, right? Those raised floors, expensive tiles, plumbing and cabling under the floor, and not really concentrating yet on optimizing the floor space or the building. That's what we started to do in generation 2. And in generation 3, we started to look at optimization and create more dense floor space, more field service in a rack, concentrate on optimizing the cooling. In generation 4, we actually started to think about how can we build a standard building block of a data center that we can extremely fast deploy. That was the introduction of the IT pack. IT pre-assembled components. Think about a container the size of a shipping container, right? Where you pre-configure hardware, server hardware, network, power, and cooling. You offload it from the truck, connect it to those main sources, and in 4 hours, 1,500 servers are up and running. Now, hyperscale actually started to really run and kick in around 2015, at least for us, with the introduction of a Generation 5 facility. And this is one single data center. 4 building blocks. If you think about power consumption, 32 megawatt of energy every hour. So think about roughly 30,000 homes consuming energy every hour. That's a Generation 5 data center. Inside, the design changed as well. Traditional data centers have very often a separate electrical room and a separate compute room. In this space, power and resources are now in the same room, close by each other, so less length of wiring, less loss of energy due to the resistance and the length of the wiring. No more expensive raised floor. Everything is put on plain concrete. And cold air from the outside is pushed in to the room to create an overpressure. And guess what? When you talk about the temperature, cold air temperature, traditional data centers had a temperature of 8 to 10 degrees Celsius. We cool with roughly 23, 24 degrees Celsius, right? And that is due that we mix a lot of the warm air coming from the servers with the cold outside air. So we reuse a lot of the warm air. In some of the areas, our data centers also reuse that warm air to heat up other buildings or parts of the towns that are close by. So the warm air coming from the servers are being reused a lot. Also, this is what we call a hot aisle, a hot pot, where we collect the warm air. It's an isolated unit, and you may notice a lot of vents behind the servers. As a default, they are not running. They can be individually activated by machine learning, artificial intelligence, and IoT devices. So the vents can attract more volume if a server is getting too warm because of heavy usage. But as a default, they are not running. To save energy, because a single fan consumes pretty much a watt, 1 watt an hour. Now, if you have 3,000 or 4,000 inside a data center, you don't really care, right? You should care, but you don't really yet care. But what if you have millions of them inside a room? Because a room, a single room like this, has the size of an aircraft hangar, where you can fit in 2 Boeing 737s, where we deploy over 60,000 physical servers. And that multiplied by 4 is over 250,000 inside a single data center. And then over 250,000 times 2 vans is a lot of energy saving by not having them all running. In Generation 6 and 7, we started to optimize infrastructure, and we started to add artificial intelligence, machine learning on top of our operations. We call that AIOps. Think about a machine learning system, an intelligent system looking for signals, looking for anomalies. And if it detects an odd behavior in any area of the data center, it starts to auto-communicate to the customer install base. It starts to do root cause analytics. It starts to look into the whole chain. What will happen if we don't respond in a certain amount of time? And at the heart of this intelligent system, we have a service, obviously, what we call brain. The brain is being fed with different signals, customers that feed into this signal system. Azure services, think about our software reports into it. Infrastructure devices, think about our hardware, our networking components. And when you think about the critical environment, you need to think about the electrical equipment, the power, the UPSs, uninterruptible power supplies, the backup generators. And mechanical, think about the cooling services, the air conditioning systems. They all feed in. So that is an optimization. because with all the respect to our smart and your smart operators, engineers, right? If you operate at that scale, you cannot just rely on anymore on human response. You need to have an intelligent system supporting that response. And then as part of research, we started to look into, is there an ability for us to build a data center that we can make resistant to natural disasters like earthquakes, hurricanes, solar storms, project native, the underwater, the submerged data center. But also the thinking was, go back to the continent of Africa, for instance, where a lot of the people, the majority, live around the coast, right? Think about 85 to 90%, where infrastructure inland is not that optimized, but where network around the continent is there. We could deploy these type of data centers very close by to the coast and have them use resources as well. That was thinking of native. Additionally, another thinking is there an ability for us to build an extreme efficient data center? And that's when we talk about PUE. PUE stands for power, usage, efficiency. Or sometimes people talk about power, usage, effectiveness. Now, quickly going back into the other ones, you see different numbers of PUE. PUE is a simple formula. You take the total facility power you buy from the grid, you divide that by what you actually deploy on the IT, on your server workloads. And the outcome, ideally, would be equal to 1, because what I buy from the grid as power, I also can use directly on my server workloads. Now, that's very often not the case, right? We all know that. Even the lights, like here, inside the data center, are disrupting that perfect score. So guess what? In 1989, we had a PUE of 2.0. That means that I lose half of the energy that I buy from the grid due to the inefficiency of the facility. Those are very often hidden costs for organizations, right? That loss of the efficiency of an on-prem facility. According to Gartner and IDC, the on-premise average PUE is around 1.76 to 1.6. Now look at where we are in a generation 7 and 8, 1.15, right? So when you translate this into money, dollars or euros, right? On every euro, I need to add 15 cents because of the inefficiency of the facility. But if you have a PUE of 2.0, you need to add an euro on every euro, right? So for the 32 megawatt facility, you need to buy 64 each hour. So PUE was also a key driver for us when we look at the efficiency of an underwater data center. Now, we don't have Project Natick deployed as an active production data center. We don't even know whether we will in the future, but already based on learnings of Natick, in the last quarter of 2020, we introduced what we call the modular data center, Azure MDC, a large container where we deploy Azure Stack hardware, hybrid hardware into it. So it can run online and offline. What does it mean? Well, if there is a disconnect in the power, it has its own onboard power module. That's the same in the network. If the network is not available or disconnected, it has its onboard satellite communication system where it can communicate into Azure Space. Azure Space, where we, for instance, work, together with the Starlink constellation, Azure Space operates in the closest ring around Earth, called LEO, Low Earth Orbit, where Azure Orbital operates in the outer ring. So the two concepts of satellites that we offer, right, have different ring connectivities. The big difference is when you run in the closest ring around Earth, LEO, that is high speed, low latency. In the outer ring, right, high latency, low bandwidth. So those are the big differences. Now, we talked a lot about those data centers. Let's take a closer look into actually how does a facility look like? Because very often the thinking is that a facility is maybe 2 or 3 data centers. Well, our facilities are almost, call it like a campus. And inside a region, we have data center campuses and other data centers around. And that's what we call the complete region, like West Europe, like North Europe, and the US. Now let me switch into another application here. And we are now in a section, a part of the West European region. This is a town roughly 75 kilometers away from the city of Amsterdam. A small town called Middenmeer. We are in an area of agriculture. Those here on top of the chute, that's what we call our greenhouses, agriculture. They are not part of the Microsoft organization, right? So we are in an agricultural environment. That's one of the reasons that we had to paint our buildings green, because we need to blend in. Another reason is that's one of the reasons why the buildings are not allowed to be higher than just 2 stories high. Now, this facility, together with another set of 8 data centers around the city of Amsterdam, roughly 75 kilometers away, so over 15 large facilities, that's the complete West European region. And you see different designs, meaning different generations. The first data center we built here is Amsterdam 05. That one is in front of us, here. Diesel backup generators at the outside. You count 9 here, 6 at the other side. So in total, 15 backup generators only for Amsterdam 05. Every data center has its own backup facility. They can all run, in case of a grid failure, a total grid failure, at least of 48 hours in a row, right, on full performance. That's the design principle. And then we have fuel being delivered if there is a need to extend. On top, you see containers, 48 of them. Those are the concepts of cooling. We take the free outside air, we filter the free outside air, we mix it with the warm air coming from the servers, as explained, right? And then we drop it. So we cool with that 24 degrees Celsius. If we are above 24 degrees, then we start to use what we call adiabatic evaporation cooling. A very old technique. The principle is the same like this. What you do, you take a sheet from the bed, you dip it in a bucket of water. Then you take that wet sheet, you hang it across the door frame. That warm air passes through that sheet and cold air actually leaves, right? That's been done very often in, for instance, the southern parts of the US, where they call it swamp cooling. That's what we do in this unit as well. We don't use sheets from the bed, right? We use what we call wet cardboard. We save, compared to traditional cooling systems, over 50% of the energy and almost 90% of the water. When we talk about water, critical component in a lot of countries as well, right? What we do here is having underground a 1 million liter water recycle retreatment plant. Recycling, repurposing the water. Capture rainwater as long as possible so that we don't have to take water from the utility companies, right? Drinkable water, potable water. We try to stay away as long as possible from capturing from them. When we talk, for instance, about another generation, I talked about the generation 5 here, you see that, hey, where are the cooling units? Well, the principle of cooling is still the same, although now it's attached to the side of the building. That way, we can faster deploy this unit, and for future, we have the ability to have solar panels on top of the roofs, not to power our equipment, but to power the facility and become part of the supply chain to the grid. in case of a need of additional grid power. You also notice diesel backup generators again, right? Different units, because this is a 32 megawatt facility. We have bigger diesel engines compared to this facility. This is a 17.6 megawatt facility. And then when we take a closer look into the concept here of networking, those smaller buildings over here, those are the core network building blocks. When a consumer connects into a region, they connect into a box like this. And we have multiple of them. And that's from a reliability, availability, but also high throughput. A big region needs to have big of these building blocks. And I'll explain somewhat more about the regional network gateways when we are at the network. Now, powering the facility is done by 60 turbines, wind turbines, to get a total of 180 megawatt of renewable energy in. So the majority of this whole facility operates on clean energy, wind energy. Now, the last generation that we were deploying over here is that generation 7, and that is a building block approach, like Lego is, right? You have a building block, like a security building block, logistics, and then compute building blocks. Based on the need and the speed to the market and demand, you attach building blocks. Now, this design can also be used as a 2 stories high design. And that's the design over here. Now, a quick view into another region, for instance, like in the US, where you can see those IT packs, those modular data centers. And very often we get the question around, hang on here, where's the building around it? Well, that was not the design principle for this. So this concept is hosting the majority of what we call our consumer services, like Hotmail, Outlook.com, like the free Skype, like the Bing search, like the gaming platform, different SLA model, different services, right? So you see the design principle here, the core, and then the building blocks. And to give you a sense of, reuse of redesigns and reuse of scale, this is a facility, single facility, and at the end here, you see the design of a generation 5 again, the generation 6, and 7 and 8. And this facility gets power from hydropower. 2 dams in the Columbia River provide the power. So let us give you a bit of sense on when we talk about a facility, a global facility, regions, reuse of blueprints, right? Reuse of information. But sometimes, right, you cannot have that luxury of reusing the designs. Like for instance in Singapore, due to limited land availability, right? An extremely expensive cost of land, we're not going horizontal, we go vertical. So this is a location-based redesign, a 13 stories high data center with traditional cooling systems on top of roof and power. So yes, sometimes you need to divert from the standard building approach. Now, when we talk about the servers, right, it's obviously, we talked about the outside, we talked about the building. What about the inside? And when we talk about servers, we at Microsoft have that, and I think a unique position as well, the ability to design and specify our own hardware. We build, design, and specify our own hardware. A lot of the specifications are also given to vendors like HP, Dell, and Novo, WinMe to build it according to our specs. And we work together in the OCP, the Open Compute Project. What is the Open Compute Project? It is a global community of technology leaders working together to unlock proprietary IT infrastructure to make hardware more efficient, to make hardware flexible, scalable, and reduce cost. Don't get me wrong here, right? I think HP, Dell, Lenovo, WinMe, etc. build really great enterprise hardware. but they build in a lot of overhead to manage their platforms. Silicon overhead, software overhead. That's overhead we, as Microsoft, don't need. So we joined the OCP. Matter of fact, OCP was founded by Facebook in 2011. We joined in 2014 with the introduction of our design concept, Project Olympus. And that is a modular design. Rack as a building block, power as a building block, right? Networking, storage. JBOD stands for just a bunch of disks, right? So a storage unit and servers. To have a high efficient, all over the world deployable building block. That's the design principle. And OCP is continued to use as a standard building block, running different services. One of the really critical services that was optimized and redesigned and reused, and that is very often also used in the space of healthcare, obviously, is an example of machine learning and artificial intelligence, where we very closely work together with NVIDIA, delivering us those high-end graphical processor units, right, GPUs, and AMD as a server hoster delivering our powerful servers. So we can deploy 8 of these powerful processors inside a single server, and that's already providing you a huge amount of capacity to run deep neural networking. But we can now also connect multiple servers together and have it act as one single AI supercomputer. And here's an example that we, when the pandemic started, right, that we helped, for instance, the Duke University in running a lot of simulations to support them with a project. Let me show you a brief video on that one.
So this all started very early on in the entire pandemic. You heard in the news every day that there was a need for more ventilators. One of our colleagues wanted to create a device to help improve ventilator capacity in splitting ventilators between 2 patients. To do that, we needed to run hundreds of millions of simulations that in total required almost 1 million compute hours. We applied to the COVID-19 HPC consortium, and then they paired us with Microsoft AI for Health. They pulled in experts, and they figured out everything we needed for the infrastructure while letting us focus on the science. By Monday morning, we had completed 800,000 compute hours and finished the entire job within 1 week of submitting the application. We used the Azure Cycle Cloud platform because it allowed for dynamic, resilient computing. We were able to get 800,000 compute hours over a weekend. It was pretty amazing to be able to submit for FDA approval less than a week and a half after requesting the compute time. We hope that having a device like this will allow physicians to have a safer way for making these difficult decisions.
And to be precise, 36 hours, not the whole 48 hours of the weekend. We run 800,000 compute hours in just barely 36 to support one of those critical components in the beginning, right? So that's to give you a bit of sense when we talk about specific hardware. Then traditional hardware, all based on that design of what we do ourselves, Olympus. It needs to be brought back to us as consumers as well, right? And that's where the network plays a critical component again. And the network is being built up traditionally. And when we talk about traditionally, we talk about switches, right? Networking components, routers. We talk about firewalls, gateways, but also a very thin layer of software on top of it, what we call software-defined networking. Software-defined networking already starts inside a single server. Inside a single server, what we do is on top of the network interface card, the network adapter, right? We apply a technology we call the FPGA, a field programmable gate array. Picture it this way. This is a chip that we as Microsoft can reprogram with our own software after it has been manufactured. And we reprogram it to accelerate the network, speed up the network, and to take away intensive workloads like encryption, decryption, certificate termination from the processor. So since 2015, this technology is applied on top of our network. That way, the processor, the network processor, can focus on networking tasks, and the FPGA focuses on security tasks and speed tasks. Inside the data center, we also manage our platform by using one single operating and management system on top of it, SONiC. SONiC stands for Software for Open Networking in the Cloud. It is an open source that Microsoft already adopted for more than 13 years ago. It runs on a Linux Debian kernel. SONiC is a networking switching operations management suite. Now, from the data centers, right, the networking, we move into those regional network gateways, the boxes I showed you at the data centers in that drone flight. They are critical because they are connected with the wide area network, that dark fiber backbone I talked about in the beginning. The regional network gateways, from a capacity point of view, they come in different sizes. The size of capacity of a network building is related to the size of the region. Almost obviously, right? Well, the bigger the region, the more services we host inside the region. The more services we host inside the region, the more consumers come in. So from a high throughput point of view, you need to have large network building blocks. Inside the network, we go over the wide area network, right? The dark fiber backbone, isolated, I talked about it. The wide area network is optimized continuously. And that's a kind of interesting discussion, right? Because you have fiber cables in the ground with a amount of capacity. Now, around 2014, we started to implement a new technology, what we call DWDM. Dense wavelength division multiplexing. Forget about the long name, right? Think about the concept here. You have that single beam of light. By using this technology, you start to split it up in different colors, and each color represents a data path. That's how you can increase capacity on existing fiber. That's what we did. And then the last mile, the critical mile, right? The customer experience mile. That's when we talk about if you want to have a secure and isolated, protected high-speed connection, you have a connection between, for instance, the hospital and our points of presence where you enter the backbone by using express route. Those are technologies and techniques being supported to make sure that a critical component like the last mile is also part of that whole overview, because all the effort you put in here, if you don't put a lot of effort in here, the experience is still that the network is not optimized. When we take a closer look at the capacity in dimensions of storage, we at Microsoft, we very often talk about standard storage, and we talk about premium storage. For us, with all respect, right? Standard storage are spinning hard drives. At the right side, you see a view of what we call a JBOD, just a bunch of disk server, where we can have 88 spinning hard drives inside a single unit. Depending on the type of hard drive, we can have up to 1.2 or 1.6 petabyte per box. We have 8 of those boxes inside a single rack. So almost over 10 petabyte per rack. Times 20, that's a storage cluster. So over 200 petabyte standard storage. Now, if we go to premium storage, flash drives, SSD-based technology, right? The small solid state disks. At the left side, we see a picture of it. We call it a JBOF, just a bunch of flash. Half a petabyte up to a petabyte of storage per single server. 42 of these servers inside a rack. That's the dimensions when we talk about the standard storage and premium storage. And that might be a lot, right? Because when you think about in this view, at the right side, you could store over 800 petabytes of premium storage, that's pretty much overwhelming in the sense of capacity, right? For a customer, a single customer. But we need to support multiple customers. And data replication, data redundancy is critical here as well, right? We need to make sure that we can replicate your data, right? So there are different layers in the management of storage, and they are different levels. So this is the connection level when you connect to your data. This is the authentication, authorized. Am I allowed? Do I have permissions? And what's the level of permissions? In this partition layer, we do a lot of consistency checking, because sometimes customers from a security point of view or performance point of view have data distributed across multiple different devices. And then the additional consistency checking is very critical. Picture it this way. I have a document with 4 pages, and each page is on a different device. That's what we call data sharding. And that's why consistency checking is critical. And then in the stream layer, that's where actually the replication of data happens. And when we talk about replication, we talk about redundancy levels. Local redundant, geo redundant. Think about geo as regional redundant, zone redundant. And when we talk about the levels, you get as local redundancy 3 replicas inside a single facility. Geo redundancy, region, another 3 replicas into another region. Zones, go back to the zone 1, 2, and 3. Every zone has a replica of your data inside a single region. If that's not enough, you can have the 3 replicas also distributed into another region. And then we talk about geo-zone redundant storage. So heavily depending on how you define the criticality of your data sets, right? You can apply different levels of redundancy to it. And that is either local, as a default, we use local, then zone, regional, and geo-zone redundancy. Now we talked about a lot of these physical assets. When we talk about physical protection, we obviously talk about data center security, right? When we talk about data center security, I first want to explain somewhat more about how do we look at security from a Microsoft Azure point of view. Look at those rings as an onion, and an onion has different layers. And the outer layer is the physical layer, right? Microsoft's responsibility, right? No discussion, building, parameter, etc. In the next ring, the logical, that's the services software. From a cloud perspective, Microsoft responsibility, end of discussion. And then we have that inner ring where the customer is, where you manage your identity and access, where you set up your own encryption, where you set up the network and management, your responsibility. So this model is basically saying that all the work we do from the outside, all the work we do in the services, still brings a bit of responsibility to you, customer, to make sure that you have proper password, you have proper governance on your encryption, etc., right? So, because if you have a website and you have a database that is open for everybody to look into, we did all the outside, right? But so my saying here is that security is still a shared responsibility in that respect. When we talk about the physical protection of a data center, we talk about the different layers we are in. I'm a data center engineer. If I need to do infrastructure deployment, infrastructure testing, or infrastructure fixing, that's when I'm at the data center. If I don't have to do one of these 3, there is no means for me to be at the data center. Now, to gain access to work at the data center, I need to go through an access request and approval. That needs to be validated by the data center operation management team, the DCOMs. If granted, I have permissions to enter the facility. I enter the facility with what we call 0 standing permissions. I'm only allowed to come onto the facility. At the facility, I will be validated. So when I enter the facility, that's basically where my journey starts, right? I enter the facility has roaming patrols carried out by security officers, perimeter fencing, video surveillance systems, and if I come in by car, license plate and car type need to be known. Sorry. I'm being watched all the time, I'm being validated, and then if I'm granted into the permissions on the facility, I report myself into the security admin building, confronted with a security officer, handing over my badge. I will be validated against the systems of record. Based on what I need to do, my 0 standing permissions go into a role-based, time-based permissions level. We work with windows of 5 minutes. I badge into the man trap, card reader, two-factor authentication. Then I'm inside the data center. I'm not inside the data center room. To gain access to the room, I need to go through a bare metal detector, data bearing device, metal detector. And if I fail to do so the first time, I will get a close body scan by the security officer. It's up to the security officer, after doing a close body scan, to determine whether I can continue my work or not. After granted permissions, I need to badge into what we call the security vestibule behind the security officer. That's a 2-door locking system. Card reader up front with the red light, inside two-factor authentication, and then hand palm, thumb, or fingerprint. Then the other side of the door opens, and at that point in time, I'm inside the data center room. Being watched all the time, in front of the rack, the side of the rack, and the back of the racks. Cameras behind me all over the place, right? So there's continuously covering, and it's not the traditional camera, don't get me wrong, right? Those are those really high-end, high-definition 360 ones, being validated all the time. Now, if I need to do some tests, I need a device, right? I get a secure access workstation, managed, controlled, operated by Microsoft, right? There is no means for me to take in my own device. Then, when I'm ready, I leave the room through the same exit. There is one way in, one way out. I need to go through the same bare metal detectors again. I need to be validated by the security officer, and then permissions to go into the admin building again, where they watch the video together with me, if I did everything correct, where they do additional checks. If everything is set to okay, 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 green, then I'm handing over my badge. I go back to 0 standing permissions. And that's the point when I get permissions to leave the facility. So this is that flow we enforce across every data center globally, right? This is the standard procedure. Part of that standard procedure is as well that we talk about segregation of duties. What does segregation of duties mean? Well, I already talked about I work on infrastructure. If you work on infrastructure, you are considered to be data center personnel. You work on the physical layer. That means that you have no access to the logical, the software layer. Service management is done from out of a MOC, a Microsoft Operations Center, outside the scope of a data center, physically away from the data center, right? There is a strict split between, if I work on hardware, I have no access to software. If I work on software, I have no access to hardware. There is a strict split between those two. Also, we test ourselves continuously. We test, we validate ourselves continuously. And that's what we use the concept of a red team and a blue team. A red team is a team that is trying to breach security on the logical layer. The blue team, obviously, is the team that needs to mitigate a breach. And in the ideal circumstances, prevent the breach from happening by pre-detection. So that's how we internally continuously test ourselves. And roughly every 90 days, and that heavily depends on the project we run, right? They rotate. So an attacker becomes a defender. a defender becomes an attacker. Learning from one is used to optimize the other. And then what we also do is, and that's a default behavior when we talk about security inside Microsoft, right? We always work on the basis of always assume breach. So a wrongly entered password is considered to be a potential breach. And that's why we have over 24 trillion threat signals analyzed a day. Think about it, right? 270 million signals per second. It is obviously that with all the brain power we have, right, we need to have a supported artificial intelligence system analyzing it. And that system is working above the concept of optics across the kill chain. It is analyzing everything, every signal coming in over the network, malware, right? Malware samples, analyzing it, going back into his own knowledge base, continuously detecting, responding, and all that information, right? We know that malware can be devastating in that respect, right? All that information is being pre-detected, analyzed continuously. And all that information is being fed back into our own defense systems, but also into the systems we provide to our customers, like data leakage protection, like security incident event management system, the defender systems. All the information every day is collected and analyzed to make sure that we have that constant security posture. That security posture needs to be validated and audited regularly, and even more regularly, right? Because of the change, the updates, and the continuously potential risk of that cybercrime attacks. And that's where we also start to support our external auditors with the product we use ourselves, the HoloLens, to be able to remotely assist them so they don't have to travel. They don't go into the data centers, right? They don't have to be physically inside the data centers, and we can have a more frequent check on all our process and procedures. And here's an example of using HoloLens.
We have auditors that are usually flying around the globe. We can't afford to be spending time traveling around. We have a technology now that we don't have to. Innovation has allowed us to still perform our audit without physically being there. That's what HoloLens has achieved.
We have to be secure. We have to be compliant. Those regular checks from our auditors help us to improve our overall security.
We have over 90 compliance standards. That's one of the biggest selling points for our cloud services. Doing assessment of the physical security of our data centers, it's 10 times easier when you've got the HoloLens and the remote assist. We can walk an auditor through the entire data center in less time, showing all the ways that we keep this data center up and running.
HoloLens units can be used anywhere in our data centers. It's a zero trust device and extremely high classification. There's 10 controls, all on the underpinning of the technology of the device, like BitLocker and encryption.
Our auditors are happy with it, using HoloLens, using remote assist.
And we're able to reduce the time that it takes to conduct and plan an audit from 6 to 8 weeks to 2 to 4. We're able to even conduct multiple audits during the same days.
30,000 hours will be estimated saved from using HoloLens and remote assist.
Yeah, we talked about 30 hours of saving, right? But also think about, not from a security point of view, but also think about environmental impact. Those auditors don't have to travel anymore. So we reduce that footprint as well. And they don't have to be physically inside the data center anymore. So we do reduce that physical access also. So HoloLens is a really great way of looking at remotely supporting, right? Still, we have that question around, okay, all that protection, physical testing, and so what about my data protection? How do you at Microsoft protect my data in the different stages that my data is in, right? Whether it's on the network or at rest or etc. On the network, we use TLS 1.2 max security, so in transit across the network. When it's stored on hard drives, intra or EES 256. In the level of the logical layer, when we talk about blobs or volumes, hard drives, BitLocker for Windows, deEncrypt for Linux, file system encryption, SQL transparent data encryption, column level encryption, gateway protection, and then also the ability for a customer to manage their own keys. Customer managed keys. Bring your own key. Store them in an Azure Key Vault backed up by a hardware security module, HSM. So when you talk about the different layers, right? Data protection, data encryption, all over the place. But there's one additional one. Let's briefly go back to 2018, when we had that discussion around the flaw of the Intel and AMD processor, spectral meltdown, the ejection of data while being in cache, right? Now, to make sure that that cannot happen, we started to look into the concept of what we call confidential compute. Protect data while being in process. That is the CPU. That's why we added the CPU. Confidential compute basically creates an isolated area inside the processor space, what we call the trusted execution environment, TEE. Now go back to the container again, that shipping container. Visualize that shipping container and deploy another container in that container that you can only open up with a unique key. That's the trusted execution environment, that isolated chamber, where you can execute code and process data. Now, confidential compute in the beginning, when we started, was supported by Intel SGX processor platform. Now, already AMD as processor is also providing the option for confidential compute. And recently, NVIDIA introduced that they are going to provide confidential compute for machine learning and artificial intelligence on their GPUs. So suddenly that spectrum of processor protection, data protection in process becomes a more common request. That's why we added it in, because we think it's a matter of time that more and more organizations will request the concept of confidential compute to protect the data. As a large section of data protection, very often we get the question around, so if you run data, right, on our storage, right, what happens with a device when it has failed? Well, as part of the data-bearing device decommissioning process, we shred the hard drives that failed. We demagnetize them, degauss, and then it goes into that large box behind in the bigger picture. The shredder, the dry shredder. We scan the hard drives because we need to have records of destruction. But what we also do, and let me briefly go back to here and then zoom in. You may notice that, see that bin next to the person who's scanning with the red and white tape, right? That's the recycle bin. That bin is inside the server room all the time. When an engineer has replaced a data-bearing device that has failed, they are not allowed to take it outside the room. They drop it in the bin. The bin is locked with 3 different locks. And the bin can only be taken out by the security officer to brought into the shredder room. And that's the only moment in time when that bin leaves the room. And that is also part of our compliancy controls, right? Data-bearing devices, when replaced, are not taken out by engineers. They go into that bin, that isolated box. This is to give you a bit of sense on, this is not very often we get that remark on marketing. You guys doing marketing in a technical session? No, we're not. Because we know that you as organizations, you have been regulated and been audited as well. This is to give you a sense of that we are audited and regulated over different categories, global, industries, region, country. Why? Because we need to be equally even more validated to make sure that we can support your requirements in that space as well. And the video talked about 90 plus. Recently, we went over 100 of different compliancy controls. And if there is interest, we can also share that link to this site where you can actually download the details around all the different compliance controls, the ISO, the NIST standards, or the GDPR for Europe, right? All those specifics can be found in here. That's about talking security. What about the environmental impact? Very often a very absolutely fair question around, Gerard, you explained a 32 megawatt data center, right? That's huge. What are you guys doing at Microsoft to make sure that you do impact that environment with that amount of energy consumption? Because those are huge energy consumers. Let's be fair here, right? Well, first of all, pretty much everybody, I think that's an assumption. That's a wrong assumption. Everybody assumes that we broadly are known as the announcement made in 2020 by our leadership team, right? That we become carbon negative by 2030. That we invest heavily in finding new means of filtering carbon out of the air, because honestly, right, we cannot just rely only on nature taking its course and support us to filter carbon out of the air, right? That's one of the reasons why we set up that $1 billion Climate Innovation Fund, for instance, to support projects like Climeworks to filter carbon directly out of the air. And that carbon might be going back into synthetic fuel production or being used in greenhouse agriculture, going in back to carbonated beverages. It's currently a really expensive way of doing so, absolutely. But you need to think about next generation and an update to reduce the cost to filter carbon, metric tons carbon out of it. And then think about, go back to the drone shot. What if all our air handling units in the future could become carbon capture units as well, right? Then suddenly you talk about 200 plus data centers globally with multiple units on top of the roofs filtering as well. That's how you need to look at these concepts. That's where we need to go to filter it out. Now, that's the ambition stated. Another part of it is, for us as data centers, 100% renewable energy usage by 2025. And then, even then, we continuously keep on testing ourselves against the on-premise average industry on how well do we do it in carbon footprint reduction? How energy efficient are we still compared to the on-premise industry? And one of the projects we run is asking an external organization to migrate over 2,000 applications from an on-premise environment into our cloud and measure the footprint reduction and the energy efficiency against each other. We can reduce almost up to 98% the carbon footprint. We can be almost up to 93% more energy efficient. However, you see there is that difference in numbers, right? Of 72 to 98 and 22 to 93. Well, that difference heavily depends on, do I migrate to infrastructure as a service? Do I migrate to platform or software as a services? That's where the big differences are from an efficiency and footprint reduction. And by the way, there is a report available for this, for those who are interested, right? And that report has been validated by external organizations and been approved as a validated report that actually goes into the little details around energy savings per mailbox. So the matter of fact is that we do pretty well in that space. Another area of environmental impact is obviously lifecycle management of our server hardware, right? So roughly every 4.5–5 years, our server hardware is going to go into disposal process. So we were still creating a lot of electronic waste because you're talking about millions of servers and then you're going about that repurposing process. Now, to eliminate that electronic waste as much as possible, we started to look into a concept of what we call circular centers. We started to do a proof of concept around 2019 in Amsterdam, in the West European region, where we actually now, when a service are scheduled end of life, we look into the hardware in, can we reuse components as spare parts? Can we reuse components to build new hardware? Can we take out components to sell to other industries to build for their own products? Circular centers, circular economy. Now, by doing so for the last 2.5 years, we saw that proof of concept in Amsterdam, we could already achieve up to 85% reuse of material. And the ambition is to reach 90%, 90, by 2025. So there is a lot of effort being done across the different categories. Where the effort done of the last years of research is actually brought into production is, for instance, in the Swedish region, where we have a data center, Design 7, Generation 7, capturing rainwater all the time for the purposes of reuse, where we run 100% carbon-free energy, where we mix outside cold air with the warm air from the servers for the cooling, where we have a circular center, where we use a different type of fuel still to run the diesel engines. I'll get back to in a second of how we think we can replace diesel engines in the future. But the diesel fuel is built out of 50% renewable raw material and has nearly an equivalent of reduction in carbon dioxide emission compared with the standard fossil fuel. So there's a lot of effort being put into. So this is an example of, optimizing the state of data centers continuously, also with environmental impact in mind. Lifecycle management of a data center. We don't run down a data center directly. We look at, can we redesign an older data center with the concept of a new design, like you see on the photo, on the picture, right? We look into redesign, and that's why we leave the building outside intact, but inside we continuously update. And if we cannot do an update internally, yes, then we run down the building and reuse the concrete. This whole concept, right, is part of what we call decades of being active in the area of environmental impact. Starting in 2009, setting our first goal, reaching carbon neutrality in 2012. Still buying certificates, absolutely, agree. And in 2012, we started to introduce the concept of what we call the internal carbon fee, the internal carbon tax. On every metric ton of carbon dioxide, as of 2012, produced internally by Microsoft, there was a tax being paid of $5 a metric ton. And over the course of the years, up till 2019, that tax was raised up to $15 a metric ton. That money is set aside in an investment fund, purchasing renewable energy, finding new means to reduce the carbon footprint, and supporting projects outside the Microsoft organization as well, with that ambition to reduce the carbon footprint. So that the internal carbon fee tax is a really great way to make people understand and support and still be able to reduce. Also, we got a lot of questions around 2018, 2017 around, you're doing a lot of effort in this space yourselves, but how can you support us customers to start to report, because we have our own KPIs as well, to start to report on carbon footprint while using your cloud services, Microsoft. And that's when we came with the introduction of the emission impact dashboard, where a customer, based on their consumption, right, can connect this dashboard, have it run, and gains insight in their footprint per service, per region, can gain insight on what did I save by not running my services on-prem anymore, but in the cloud, and can download their own data, because it is based on their consumption, and do their own reporting on it. So the emission impact dashboard is a dashboard that can be connected to your Azure services to be able to report the consumption and the footprint reduction and the footprint you create by running the services in the cloud. Now, this was in the beginning only for Azure and Dynamics, and recently we started to do a preview of the ability to report also when you run 365 workloads. Think about Mail, think about SharePoint, think about OneDrive. Now, that brings me into the last section. The last section is talking about what are we doing in the area of research? What is Microsoft doing, for instance, in the area of, optimizing the supply chain of power? There are reports that define and state that in this section of energy transformation and transport, we lose roughly around 65% of the energy before it even hits a facility like a data center. And this is what we do for decades. And the majority of the loss very often happens at this section, right? And that is due to the quality of the substations, the quality of the wiring, and the distance it has to travel. Now, Microsoft Research started to look at how can we simplify this by starting to introduce a concept of what we call a fuel cell technology. The fuel cell is a box with a unit in it, a chemical unit, filter unit in it, and a membrane unit in it. For those who are technically interested, we're talking about a solid oxide fuel cell. This cell is directly connected to the rack because when we inject it with gas, the output is direct current. So there is no need for conversion from alternate current into direct. Absolutely a reduction in cost, risk, and less complexity, efficiency gain over 50%. However, still a tiny amount of carbon dioxide, right? So that's when we started to look into, is there an alternate source of input? Yes, we found one in hydrogen. Hydrogen built up by using wind and solar power, not the traditional way, right? Because that's a really dirty process. I absolutely agree. Hydrogen being injected into the fuel cell, and this is a different type of fuel cell, a proton exchange membrane, doesn't create any CO2, carbon dioxide anymore. It is extremely efficient and is able to power up extremely fast. And that's one of the reasons why we start to look at, can we in the future replace our diesel generators with hydrogen fuel cell backup generators? And we're currently already testing and running tests. This was the first test for Daimler-Benz engines running on hydrogen. Now, 1 megawatt fuel cell supporting a single room running as backup power. Still, right, in between, for you actually get into fuel cell technology, in between, we're looking at running our diesel generations on biofuel, or also looking at, and I always explain it like this, large Tesla battery packs, right? Tesla on steroids, so to speak, running as a backup facility and not having the diesel backup generators anymore. Because as part of that 2030 ambition, we also want to have diesel-free facilities. Now, going back to hydrogen, even with the current, devastating happening in the Ukraine, right, that gas brings a lot of process thinking in a lot of organizations and governments and countries of the hydrogen economy. Microsoft already saw in that concept a while ago that there are still challenges in that space. And two big challenges we also see is that how do you store that amount of hydrogen at a facility to run a data center facility like Amsterdam, Middenmeer, right? How do you build up that amount of hydrogen on a daily basis by using only solar and wind power, right? Those are still challenges we face. So will this be solved within a year? No, this is a longer run of the project. Like, think about the marathon project, but already a lot of learnings came out of, for instance, if you start to store hydrogen in ammoniac, it is less dangerous, right? So the evolution is starting, the revolution is starting, but there is still a lot of work to do. And that's when we more and more need to work together as organizations. Another large research project for us is to look at moving away from air volume, airflow cooling for those high-end processors into liquid cooling. As we see that at some point in time, you cannot push that volume of air inside the room anymore with all that vents blowing and pushing without creating any damage. So we started to look into, what if we use microchannel cold plates technology? This is a technology that you basically apply cooling ribs, cooling units with liquid on top of the processors and a tube system to circular it, right? Extremely efficient, but you need to extend hardware with additional hardware. That's the same in the space of when you do what we have in a car. You create a heat loop system, liquid on the motherboard, and then a tube system and a heat exchanger. Also absolutely efficient. However, extension of hardware. So we changed the thought process. What if we strip down a server completely with its components, only have that part of the motherboard and the power unit, and just dip it in a unit of liquid. I'm not talking about water here, right? I talked about liquid. Because if you drop a system like this in water, you blew out every circuit. This liquid is a non-corrosive, non-toxic, critical, non-conductive liquid. Has an extremely low boiling point, 50 to 57 degrees Celsius. Extremely efficient, so efficient that we could easily overclock the processor without any thermal issues. Inside the liquid, completely isolated, so we saw a drop of hardware failure of 12x drop in hardware failure, 12 times less hardware failure. So this two-phase immersion testing went into pre-production testing in one of our data center facilities, where we actually run a large container with only liquid cool hardware, and we can run more servers in an immersive liquid cooled tank than we can to a traditional rack. This is now the complete server. So an extremely efficient way for us to look at. Also, if this might be usable on a broader scale, think about that data center in Singapore, where we have the traditional cooling systems, right? Energy consumers, water consumers. What if we move into liquid cooling over there? We don't need those units anymore, right? Saving a lot of energy and water, right? So that's another thinking process behind it. When we talk about data, think about data in the concept of storing data as a hologram, right? Digitally stored. One of the projects we do when we talk about holographic storage is, can we store data as a hologram in a crystal to overcome that growth of data? We can reach 10 times the read access rate compared to a spinning hard drive, multiple times the density of a hard drive. We can write, read, and erase a hologram, right? The erasure happens by using ultraviolet light. It's now a matter of time for us. Is holographic storage still futuristic, science fiction, or can we build it in such a way that it can be used at scale? Now, from a concept of archiving, journaling, right? We also looked into a project, what we call Project Silica, and that's storing data in glass, right? And that is from a archiving purpose point of view, you can store a lot of data in glass, right? And have it there for thousands, 10,000s of years, records, right? If you store it offline, you're not wasting energy. You just store it there. If you need it back, you read it in. So that's the thinking of storing it in glass. But there's another interesting project going on, and that's what we call Project Palex. And that's to overcome that huge data gap we foresee towards the future. And this is where we look into, is there an ability for us to actually store data as synthetic DNA? Project Palex is started to basically work to transform the bits into bases and have the bases transform into a synthetic DNA string, right? I don't have to explain that the purpose of DNA is to store information, right? Absolutely. And we also have that ability already of decoding it back. Why? Why synthetic DNA? Density. We think we can reach density so much more that we can store a zettabyte of data into a data center rack. Now picture it this way. The current complete internet from its data corpus point of view, the set of data, the current internet, and that's the prediction, would be able to fit into a shoebox of DNA. That's the density we're talking about. And if you think about, well, how would such a system look like, right? We currently have a fully automated system. Now, I don't see this actually being operationalized in a data center yet, but the thinking here is that we can already automate the different stages, right? The synthesis again, the prep and the storage, and the decoding. So we are already, with universities and other organizations, testing and validating and moving forward. And then last, but definitely not least, questions around what's Microsoft doing in the space of quantum computing, right? Now, I have a very short brief video at the end of this talk track. But first of all, when you look at the space of what we did for the last couple of years, there's a section in the video of talking about what did we achieve up till now, and what is that we recently achieved, and what we think will become the future of quantum. Now, also, there was a project called Project Gooseberry, and that is reduce the complexity of the quantum controller. This is the traditional quantum computer controller that was used for a couple of years ago. You see that blue wiring that is going back into all the computers that do the prep work, the front work. The last section that I'm pointing out at, that is basically the wiring around the qubit, the quantum qubit controller. Now, this is the result of a couple years of hard work with research in universities and labs to reduce the complexity of the wiring and the complexity of the controller itself. And that's Project Gooseberry. That's what we achieved together with others. Additionally, on top of that, we introduced the concept of our own Azure quantum platform. And let me show you a brief video of the research we did, what we did up till now, and what are we doing towards the future.
By deepening our understanding of how quantum computers solve intractable problems, we've made breakthroughs that enable quantum solutions to run on classical hardware, yielding immediate advantages. And what's exciting is that those solutions will be even faster when run on full-scale quantum computers.
We've made breakthroughs in cryogenic engineering, open-sourced our quantum development kit and programming language Q#, and we've introduced a full-stack open cloud ecosystem with Azure Quantum, bringing forward quantum solutions, software, and hardware.
Quantum computing. The power of 1 qubit times 1 million. The potential to solve the world's most complex challenges. Achieving millions requires a design that is scalable, protected, and reliable. We've harnessed that potential. The Majorana, a near-century-old theory. Until now. Moving beyond the experimental stage, we've engineered topological devices with the power to control a new phase of matter. Bringing Majoranas together, we've unlocked the first step, one topological leap towards 1,000,000 qubits. Developing a full stack solution and the birth of unlimited potential.
So that's the thinking behind, at least at Microsoft, that if you want to build a scalable, right, performance quantum computer, you need to start to thinking in topological qubits. And that's why we went that way of the topological qubit, right? No need to say that in this current research, right, there's a lot of work around quantum computing being processed, reported, and be written. You don't know whether that you're going in the right track, but this is the way we think is moving forward, right? And that's with the Majorana. And that brings me into the last piece of the whole presentation, and that is to give you a link to this website. And this website is background reading in the areas of interest, right? So if you are interested in that space of, you know, what about the data center futures? What are you guys else doing? Project Natick, more details around the submerged data center. DNA storage, this is storing data as a hologram, storing data in glass. Liquid cooling, right? Fuel cell technologies can all be found here. For those who are very intrigued in the space of environmental impact, that cloud carbon benefits brings you down into that report I was talking about, right? The details in the reports, the dashboards that you can connect and start to gain insight, emission impact dashboards, right? More information about how we look at the ecosystems, what is a circular center in more details, right? How do we think about the different scopes? For those who are more looking at, you know, the compliance and controls around, you know, the data centers and in relationship to your own healthcare, compliance identification, that is the one when you click on it, you go into that PDF, and then you can download the whole book and go into the nitty-gritty details of, you know, what services are covered, for instance, on the ISO 2711001, what has been audited, what services are part of it. There is a lot of additional details and reading. When I talked about the digital defense report, that is when we use that intelligent system to detect malware. What did we do with malware, right? The attacked our ransomware kits, right? What did we scan? What did we do? How do we overcome? All that information can be found over here. And then there is a section on, if there is interest in understanding, for instance, the HoloLens concept, right, on operations, understanding in more detail about what about Azure Orbital or Space as a backup in a network, for instance. And then for those who are interested in the designs of how do I set up, how do I make sure that when we run services that we have them reliably running across zones, paired regions, and how do I still make sure that data residency protection is there? So this website is there to be shared, and I'll definitely, what I will do, I'll share a PDF format of the deck, and I'll share the link in an email with you, Sandra, so that you can distribute it to the installed customer base. Make sense? And that brings me into, first of all, I hope I gave you somewhat more insight in what it is when we at Microsoft talk about cloud and what is under that hood, right? You're consuming services, but what's happening below. And with that, I think if there are questions, we're now open up for Q&A. I see questions, but they are in Portuguese, so I think somebody needs to help me translate them.
Yeah, I'm sorry, Chair, I'm in mute. We have one question, but this question is probably is to answer Sandra or myself, but Sandra will answer the question. Okay, it's more about hospitals in Portugal.
Oh no, okay. Just answer it in your own language.
Okay,
no problem.
Okay. Thank you. Temos aqui uma pergunta do engenheiro Nuno Miguel Ferreira, da Altice, em que diz: bom dia, para quando o recurso a arquiteturas de cloud computing públicas ou privadas nos hospitais EPEs? Sandra, não sei, queres pegar na questão?
Eu posso pegar, e obrigada pela pergunta. Felizmente nós já estamos a ver em muitos hospitais públicos a adoção de tecnologias cloud, nomeadamente para complementarização daquilo que é os atuais data centers, e temos já vários casos de uso de utilização da nossa cloud Azure, precisamente em alguns dos data centers de alguns hospitais em Portugal, e eu acho que até é a melhor forma de dar, e estamos progressivamente, nós Microsoft, estamos diariamente a ver com estes hospitais este recurso cada vez mais a estas arquiteturas, e acho que é um caminho que estamos a fazer ainda de alguma forma lentamente, mas que está a acontecer. Eu diria que para ilustrar um bocadinho melhor o que é que estamos a fazer, nós temos amanhã uma sessão às 12 horas com 3 entidades de saúde, o Centro Hospitalar de Trás-os-Montes e Alto Douro, a ARS Norte e o Centro Hospitalar de Lisboa Central, onde teremos precisamente a partilha pelos responsáveis de tecnologia dessas 3 entidades de projetos que estão a fazer connosco, já utilizando tecnologias na cloud e trazendo a cloud como complementar àquilo que são os data centers que existem hoje nestes hospitais. Portanto, uma forma até de mostrar como é que isto está a acontecer é ver amanhã essa sessão. Dito isto, engenheiro Nuno, eu reforço que temos que ver isto de uma forma mais abrangente cada vez mais, e que também nós na Microsoft achamos que há ainda muito trabalho para fazer nos hospitais e que esse trabalho tem que ser feito em conjunto, não só por nós, Microsoft, um dos providers que pode prestar esse serviço, como também a Altice, mas trazer também os integradores e os próprios hospitais para fazer essa modernização. Obrigada pela sua pergunta.
Não havendo mais perguntas, não sei se no chat não entrou mais nenhuma pergunta. Não sei se queres fechar a sessão, Sandra.
Sim.
Agradecer aqui ao Gerard, primeiro. Gerard, great presentation, very explicit. You have to invite us to visit a data center physical.
Just to be there in presence, yes.
Yeah.
Thank you, Gerard. Thank you for your
Thank you so much.
presentation. I'll switch. I will do the closure, but I'll switch to Portuguese. Is something, and you talked about the documents that you are about to share. What I will do is, once you share it, I will put it in our stand here at the conference so that people can go there and download it, okay? And also the links. Thank you.
I'll make sure you have it directly after the session.
Thank you very much.
Thank you, Gerard.
Okay, I'll switch to Portuguese. Estava a agradecer ao Gerardo, obrigada também ao Miguel. Nós esperamos que esta sessão tenha transmitido a todos que nos acompanharam aquilo que é uma visão, obviamente resumida, da modernização tecnológica dos nossos próprios data centers. Tivemos a oportunidade de ver durante a sessão aqui uma visão histórica de como é que fizemos esta evolução, aquilo que são as várias gerações do data center, daquilo que é o trabalho que fazemos todos os dias, de integração no meio ambiente, com aquelas visitas virtuais que o Gerardo nos mostrou, dos temas de componentes de segurança, de privacidade e também de compliance, bem como agora mais para o final, aquilo que são as constantes inovações, e eu acho sempre muito cool o liquid cooling, aquelas que são as inovações que estamos constantemente a perseguir para maior eficiência e tornar cada vez mais sustentável também aquilo que é a nossa pegada ao nível dos data centers. E desmistificar também aquilo que é este discurso dos data centers na cloud, o que é efetivamente a cloud, e esta sessão também tinha esse objetivo de trazer. O título desta sessão vinha no formato de uma pergunta que equacionava esta relação entre aquilo que é a modernização tecnológica e os novos modelos de governação. E efetivamente é nossa convicção na Microsoft que estes avanços tecnológicos, aquilo que estamos a ver do ponto de vista daqui da gestão do data center, mas que simula também o que é a gestão de cada data center dentro das entidades hospitalares, que desafiam aquilo que são os modelos de governação comuns, e que temos que ter modelos de governação que se adaptem a esta velocidade e às exigências do mundo cada vez mais digital. Quer seja na gestão de cada data center nas entidades, que seja mais on-prem, que nós chamamos mais on-prem, ou nos data centers híbridos, que complementam aquilo que é os atuais data centers com estas capacidades de cloud, mas também naquilo que é a crescente e constante adoção destas tecnologias que existem na cloud, exigindo, naquilo que é a nossa visão, cada vez mais modelos de governação e de partilha de risco com outras entidades, nomeadamente com entidades como a Microsoft e com outros providers. Acreditamos que só esta partilha de governação, esta partilha da tecnologia pode suportar aquilo que é a velocidade que é exigida e que se tornou ainda cada vez maior naquilo que é o setor da saúde, nomeadamente nos últimos 2 anos que todos vivenciamos. Quero agradecer a todos a vossa presença, quero convidar-vos a visitarem o nosso stand, lá podem contactar-me a mim ou ao Miguel diretamente, e podem ver também alguns dos vídeos onde mostramos também aquilo que são as nossas capacidades Microsoft para a saúde. E reforço aquilo que já disse há pouco na resposta à pergunta que nos foi feita, o convite para a nossa sessão amanhã às 12 horas live, onde estaremos a partilhar convosco, mas aí na primeira pessoa, 3 exemplos de soluções tecnológicas que partilham também desta utilização da cloud e que serão apresentadas pelo Centro Hospitalar de Trás-os-Montes e Alto Douro, pela ARS Norte e pelo Centro Hospitalar Universitário de Lisboa Central, e que serão certamente muito interessantes para ilustrar a utilização da tecnologia por estas entidades e desta tecnologia de futuro. Fica o convite, ficam também os nossos contactos. Como disse, eu vou colocar a informação que o Gerardo vai disponibilizar no nosso stand para que vocês possam fazer download, e obrigada a todos pela vossa presença.
Obrigado.
Obrigada.